Hi class. In today's video we're going to be talking about section 2.1, Reasoning and Logic. And so we're going to dig into this because eventually we're going to be starting to talk about proof and how we know things whether they're true or false. And what this is going to give us is the basic foundation for determining if, say, one thing is true and another thing is true, how do we know that they're true together? Or if something's true and something else is false, taken together, is that true or false? And this is really going to set the stage for implication. So, like, if something, then something else. And so these are some of these basic logical structures that we'll use in proof throughout the course. So on this slide, I have two bins. I have statements on the left and not statements on the right. And so I invite you to maybe take a minute and look and see what do you think is, or what is common to those things that ended up in statements? And can you find anything that's common to the things that aren't statements? So maybe pause the video now and think about that for a minute. And so what it turns out is that statements are essentially, or they're like sentences, but they're something that either has a truth or a false. So if we look at a statement, it has a value that's true or false, but not both or not neither. So all students like hamburgers. Well, certainly that's not true, but we can decide if that's true because we know who all students are, whether they're in elementary, middle, high, or college, or right, and whether they're here or in other countries. We understand what all students are, and we can decide if they like hamburgers or not. Similarly, 2 plus 3 equals 5 is a statement because we know what 2, 3, and 5 are. We know what the addition sign means and that the equality sign is asserting that those two quantities are the same. And so we can determine that that's true. In the third one, there exists a natural number n such that 3n equals 6. Now, we might not be familiar with the phrase natural number off the top of our head, but those are those numbers 0, 1, 2, 3, 4, and so on. So starting in 0 and counting up. And we can determine, is there a number n for which that's true? Yeah, well, when n equals 2, 3 times 2 equals 6. Similarly, some people like mathematics. We know what a person is. And we can evaluate that's true. Some people do like mathematics. And then the last one, for all natural numbers n, 3n equals 3n. Well, again, we've defined the natural numbers, and we know that 3 times a number is always going to give us the same thing as 3 times a number, right? Those two sides will always be equal. Now contrast that with these ones that aren't statements. She has blue eyes. Well, who is she? We don't know who she is. It's ill-defined. It's not specific enough, so it's not a statement. Similarly, we have x plus 7 equals 18. Well, we want to be like, well, x is 11, but we haven't defined what x is. So contrast this with the two that used n on the left. We said there exists a natural number n. So if this had said, let x be an integer, or let x be a whole number, or let x be a real number, like if we had defined what x was, we could evaluate its truth value. But if the thing that came before this said, well, let x be your favorite color, well, then green plus 7 equals 18 doesn't mean anything. And so statements have to be fully defined. They have to be able to stand alone. There can't be any ambiguity. And we need to be able to resolve it to either a truth value or a false value. And so here's our definition. A statement is a sentence that is either true or false, but not both. And so notice it says sentence. That's often why in elementary school you'll hear things like 2 plus 3 equal 5 be called a number sentence. And so that's a phrase that you can start to be familiar with. And so we'll often be like, well, let P be some statement. So like, all students like hamburgers. Then the negation of P, or the opposite of it, which is denoted with this not symbol. So you're trying to draw over and down like that. Not P means not, or the negation of it. And so the book is going to use this tilde P, but I'll use this not symbol. I think that it's a little bit more common to see it used in math contexts. So let's go ahead and work with this notion of negation. So remember we said that a statement has a truth value. A statement is either true or false. 2 plus 3 equals 5. That is a true statement. All students like hamburgers. Well, we said we defined who all students were, but we didn't say that it was true, right? We said it was false. Right? So we know that all students like hamburgers is false. There exists a natural number n such that 3n equals 6, we said was true. Some people like mathematics is true. And then for all natural numbers n, 3n equals 3n was also true. So the negation means not. So if it's not true, it's false. And if it's not false, it's true. False, false, and false. Now, let's try to translate these statements into the negation. So 2 plus 3 equals 5. Well, we could say 2 plus 3 does not equal 5, which is a false statement. There exists a natural number n such that 3n equals 6. And so it's important, and I'm going to write this in a different color. There exists, the negation of there exists is for all, or for none. So, there exists a natural number n such that 3n equals 6. We could say there is no natural number n such that 3n equals 6. Or you could say, and I'm going to write this and then I'll erase it, for all natural numbers n, 3n does not equal 6. Right, so you can see how they're equivalent. For all of them, it isn't equal. Or there's no n such that it is equal. And I would say I probably actually prefer the second one, but I don't think I can easily drag that one up there. So we'll leave that first one there. And then we have, oh, and that's, I got ahead of myself. Because the next one is all students like hamburgers. So all, the negation of all is, instead of all do, there are some. All students like hamburgers. Well, the opposite of that is there are students that dislike hamburgers. Right? So if everyone likes them, the opposite of that is that there are some that dislike them. And so now we have this. There exists a natural number n such that 3n equals 6. Well, now we can say for all n, 3n does not equal 6. Some people like mathematics is true. So just like there exists went to some, when we negate some, we say all people dislike math, right? Which we know is not true because, I mean, at least I like math and I'm a person, so there's a single counterexample. And then lastly, for all natural numbers n, 3n equals 3n. So the opposite of all is some. For some n, 3n doesn't equal 3n. Or you could say there exists a natural number n such that 3n doesn't equal 3n. And now we know that's not true, but that lets us at least talk about that. I'm going to move myself down a little bit so I don't cut off the corner. Oh, but now I'm like, let's see if I can get, there we go. And so this is something that we'll practice and we'll get more comfortable with working between there exists and for all and truth values. And so here I have them typed up much more easily to read. So we had 2 plus 3 does not equal 5. Some students dislike hamburgers. For all natural numbers, n, 3n doesn't equal 6. No people like mathematics. And there exists a natural number n such that they aren't equal. And so it turns out that when we're working with a lot of truth values, it's going to be a little bit easier if what we do is we start to put them into tables. And so remember, if P is some statement, so P is a statement like 2 plus 3 equals 5. Well, if that's true, its negation is false. If it were false, its negation were true. But what if we're working with more than just one statement? Like, what if we want to say, like, 2 plus 3 equals 5 and 3 is bigger than 2? Or we wanted to say or, so 2 plus 3 equals 5, or 3 is less than 7, right? What if we want to work with more than one? And so that gives us our conjunction. And so conjunction is and. P and Q, which we write P and then like this little hat, it's the caret, Q. So we read that P and Q. And so if P and Q are two statements, so notice that we don't have just one anymore. So P and Q are both statements, meaning they're either true or false. Then the conjunction of P and Q, which we write as P and Q, is true if and only if both of them are true. If one of P or Q are false, or if both of them are false, then P and Q is false, right? So notice I read that as P and Q. So that's our and this, our definition for or is our disjunction, P or Q. And so I will read that as P or Q. If P and Q are both statements, then their disjunction, denoted P and then like an upside down caret, or almost a V, P or Q is true if either P or Q or both are true. And P or Q is false if and only if both of them are false. And so let me summarize this in table format. So first we know that P can be either true or false. And you're like, well, now why did you write two trues and two falses? Well, if P is true, we either have Q is also true or Q is false. And then if P is false, well, Q could be true or Q could be false, right? So for two statements, P and Q, there are four possible combinations. That they're both true, that P is true and Q is false, P is false and Q is true, or they're both false. And so our definition of conjunction, P and Q, was that it was true if and only if both P and Q were true. So in our first row, P is true and Q is true, so P and Q is true. P is true, Q is false. Well, that means that P and Q is false. In that third row, if P is false and Q is true, P and Q is false. And then the last says false and false, and so that is false. And so now, go ahead and repeating. We know there are the four combinations: true, true, false, false, true, false, true, false. And it says P or Q. Our definition of disjunction was that P or Q is true if P is Q, if Q is true, or both are true. So in our first row, they're both true, so it is true. In our second row, P is true. It doesn't matter that Q is false. One of them was true. Similarly, in the third row, Q is true, which is enough, but then the last one is false. And so we see that pattern for P or Q. And so I had my nice neat type version there, true, true, true. So I'll look at the conjunction side first. If they're both true, it's true, but otherwise they're false. And then over here, if one or the other is true, P or Q is true, but if they're both false, it's false. So go ahead, and I would say after I introduce this, pause the video and work through this. We have three statements. P, which is 2 plus 3 equals 5. Q, which is 2 times 3 equals 6. And R, which says that 5 plus 3 equals 9. First, classify P, Q, and R as true or false. And then I want you to classify, so what are each of these? Oh, my pen went away. Each of these, are they true or false? And then classify each of these values as true or false. Remembering that P and Q will be true if they're both true, and Q or R will be true if one or both are true. So P, 2 plus 3 equals 5, is true. Q, 2 times 3 equals 6, is also true. 5 plus 3 does not equal 9, so that is false. So P or Q, then, is true or true, which we know is true. Q or R is true or false. Remember, or only needs one of them to be true. So we have not P, so not true or false. Well, not true is false, so false or false. And for or to be true, one of them has to be true. And then here we have not P, so not true, and not Q, which is true. So not true is false, and not true is false. False and false is false. So notice that this next one is a little different. It says find P and Q together and then take the not of it. So not, P was true and Q is false. And we know that true and false is false. So we have not false, which is a true statement. Right, and so that shows us that these two rows, not P and Q and not P and Q, are not equivalent, right? Those are not the same sentence. Now we have P and Q or not R. So P and Q, so we have true and true, or not R, which was false. So then we have true or true, which is true. And so working with these truth values and these truth tables is something that with practice will become more familiar. And so here we have those typed up. So we had true, true, false, 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 true, 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 false, false. Ooh, what did I do mistakenly there? P and Q. P and Q. Ah, do you see what I did? Q is true. P and Q. True and true. True and true is true, and not true is false. And so see, it's important that we're careful. I mean, mistakes will happen, whether you're a professor or a student. But there we go. We see that when we fix that, and that's why I like to type things out ahead. Not true is false. And so now it matches. So this is maybe looks daunting. It's a wide table. But let's go ahead and we'll work on it together. So remember we talked about P and Q. If we have two statements, there are four possibilities. True, true, false, false, true, false, true, false. You don't have to write those rows in that order. I just do it that way because it's easier for me to keep track of all possibilities. Well, Q can be true or false or true or false. And actually, I'm going to rewrite this because this way might make more sense. So we know that Q can be true or false. And then for each of those, P could be true. We also know that Q could be true or false, and for each of those, P could be false. And so that's another way we could write it. And so we had our AND table, P and Q, in a previous one. But true and true is true. True and false is false. False and true is false. And false is false. And now the not is just a matter of negating this previous column. So true becomes false. False becomes true. False becomes true. And false becomes true. And then if we look at the or, and so now we have to go look back at those first two again. True or true is true. True or false is true. False or true is true. False or false is false. And now negating that column, true becomes false, true becomes false, true becomes false, and false becomes true. And now we're going to negate our very first two columns. So we had true, true, false, false. So we have false, false, true, true. And then we had true, false, true, false, which means we have false, true, false, true. Notice we still have all the combinations. They just changed places in our list. And now let's find the and of these. Not P and not Q. We have false, 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 true. And not P or not Q. We have false, true, true, and true. So take a minute and look at this table. Do you notice any patterns? Do you see anything that maybe, are there any columns that are the same? Well, notice this column, not P or Q. Well, that's the same as not P and not Q, right? Because that's false, that's false, and that's true. So that means that not P or Q is the same as not P and not Q. So here we would say that those are logically equivalent. And then there's one other column, pair of columns that match. Not P or Q, or no, I said that wrong. Not P and Q, and not P or not Q are the same. So not P and Q is the same as not P or not Q. So remember in that previous table we said that we couldn't just distribute, or it wasn't the table, it was that sample. We couldn't just distribute that negative through that negation, that not. What turns out happening is that if we have the not of an and, we get the or of the nots. Or if we have the not of an or, we get the and of the nots. And these two relationships, which are marked here, that these columns are the same, have a special name. And these are called De Morgan's laws for logic. De Morgan's first law says that not P and Q is not P or not Q. And the second law says that not P or Q equals not P and not Q. And so that table we had with all of those columns and showing that those two columns were equal in the case of this first one, and showing that those two columns were equal, and in showing those two columns were equal, is actually the proof of this law. Since the columns for the negation of the conjunction, so negation of the conjunction, and the disjunction of the negations, were equal in every instance, they must be equivalent. And I'll switch to a second color. And since the columns for the negation of the disjunction, and the conjunction of the negations, were equal in all four cases, they must be equivalent. And so whenever we're proving things are true in terms of logic, we often use a truth table, because that shows us exhaustively in every possible combination of truth values whether or not they have the same resulting truth value. Now let's consider a story. Your friend Betty is excited about a potential promotion at work, and she says, "If I get a raise, then I'll take you to dinner." I mean, Betty's a wonderful friend. So under which of these circumstances could you be upset? If she gets a raise and takes you to dinner, you're like, well, thank you. So you certainly can't be upset at her there. Now, if she gets the raise and doesn't take you to dinner, then you can be upset, right? Because she lied to you. Now, if she doesn't get the raise and takes you to dinner, well, Betty's a really good friend, and you need to hang on to her. If she doesn't get the raise and doesn't take you to dinner, well, you can't be upset then either, because she didn't say anything about if she didn't get a raise. And so I use this story to illustrate our conditional. It says, if I get a raise, then I'll take you to dinner. And so if P is a statement, we call that the hypothesis. And if Q is our other statement, we call that our conclusion. And symbolically, we would write P implies Q, or if P, then Q. So you could say, if P, then Q, or P implies Q. And so here, if she gets a raise and takes you to dinner, you're okay. If she doesn't get the raise and takes you to dinner, you're okay. Well, you're more than okay because you got free dinner. If she doesn't get the raise and doesn't take you to dinner, you're okay too, because she didn't say that she would. So the only time P implies Q is false is if P is true and Q is false. So P implies Q is false if and only if. So IFF is if and only if. P is true and Q is false. And so we'll work with this a little bit. And I know that there's a lot of new things going on in logic because it's likely that this is the first time that this is when you've been taking a formal logic course. So, since an implication has a truth value, it's an example of what do we call something that has a truth value? We call it a statement. And if P implies Q is a statement, then we have some special names for other relationships. If P implies Q is a statement, then we call its converse Q implies P. We call its inverse, so the negation of each of them, not P implies not Q. It's contrapositive, so not only are we taking and flipping the order, but we're negating it. Not Q implies not P. But let's look at what happens with these truth values. So this column here, P implies Q, is just my copied one. So Q implies P. So if Betty gets the raise and takes you to dinner, we're happy. If she doesn't get the raise, we're fine. If she gets the raise but doesn't take you to dinner, we can be upset. If she doesn't get the raise, she doesn't have to take us to dinner. So certainly it's not true always that P implies Q is the same as Q implies P. So we can't say if she took you to dinner, then she got you a raise, right? That's not how that implication works. And then if we look at the negation here, not P implies Q. So false, it doesn't matter what she does. False, it doesn't matter what she does. She got the raise and didn't take you to dinner, we'll be upset. She got the raise and she took you to dinner, we're good. I'll pick a different color for this last one. Now not Q implies not P. So she didn't get the raise, so we're okay. She got the raise and didn't take you to dinner. Well, then we can be upset. She didn't get the raise, so we'll manage. She got the raise and she took you to dinner. So just like on a previous slide, do you see any patterns? Are there any columns that are the same? Are there any things that are logically equivalent? Well, P implies Q is true, false, true, true. And our last one, not Q implies not P. If you remember, that's called our contrapositive. So an implication and its contrapositive are logically equivalent. And then we also see that Q implies P is the same as not P implies Q. So here we have Q implies P was called our converse, and not Q, P implies not Q is our converse? No, inverse. Our converse and inverse. So converse and inverse are logically equivalent. Remember, we say two things are logically equivalent if their columns are the same in our truth table. And so again, there's a cleaner version that shows the equivalences. The most important one to remember is that an implication and its contrapositive are equivalent. And that's the one that we'll use most often. Because Q implies P and not P implies not Q, that is really just that, contrapositive. And so, right, the thing I want you to remember is that P implies Q is equivalent to not Q implies not P. And so we had a lot of new terms in this section. We had a statement, which is a sentence that is either true or false, but not both. A negation, which is when we take the not of something. A true becomes false or a false becomes true. And when we took the negation of for all, we would say that there exists something for which it isn't true. Or if we'd say that there is a case where this is the true, the negation is for none or for all that isn't true. A compound statement is when we link two statements together, and we can link them together either through a conjunction, an and, or a disjunction, the or. Conditionals or implications were like our if P then Q. The P portion of a P implies Q is a hypothesis, and the Q is the conclusion. And we had the converse, the inverse, and the contrapositive. And it's important that we remember that a conditional, if P then Q, is logically equivalent to its contrapositive, not Q, then not P. And so I know that with practice, this will be a little bit more comfortable. And on the homework, you'll see a number of truth tables where you're going to be working with your conjunction, your disjunction, your implication, and negation. And so I'll see you in the next video, everyone.